Hello, this is Mr. Wilbert. This is his second attempt at trying to do a lesson here on graphing piecewise function. I realized I made a mistake earlier, so we're doing round two. We learn from our mistakes, hopefully. So what we're going to look at today, specifically just for this video, is how can we graph given a piecewise function table. So far in class, we've worked on if I give you the function table and the graph, can you connect the two? If I give you the graph already, can you then construct the functions? So here what we're looking at is if I give you just the functions, can you construct the graph? So that's what we're going to look at today. We're going to look down here at one of the examples we have further down the slides. And so looking at this, I can see it's a three-part function, three-part piecewise function. So that means I'm probably going to have three different graphs on three different functions on this graph. Now, when I start working with this, I generally kind of say to myself, okay, let's see how many functions we have and what do we need to work with. Now, when you're working with these, it really comes down to how comfortable you are with functions themselves. I mean, can you recognize which one's a constant function, which one's a quadratic, which one's linear, etc. And if you're really comfortable with those, it makes the graphing aspect pretty easy. If you still struggle with a little bit, that's okay. I'm going to kind of show you kind of a step-by-step watered-down version you could use. That might take a little bit more time, but it's pretty good at getting you the result you want. So with that being said, let's give this a shot. So looking at this function, I've got three different functions I have to work through. And so I'm going to say function one, and we're going to work on that one down here. Now looking at function one, I actually can tell it's a constant function. And because you can recognize hopefully that we have a 3 here, and that means there's no x value, so it's a horizontal line at 3, starting at -2 and ending at 2. And to graph that should be pretty simple, but let's kind of say you weren't quite comfortable with that, and you kind of want to see kind of a process you could use. So the way I've kind of done it before in the past is I constructed a quick table, and we have our x's on one side and our f of x or y values on the other. And all we're going to simply do is use this domain to kind of act as input values for our functions there. So if we look at it, our first input value we possibly have is -2 for x, because that's our domain. Now, normally we'd say, okay, let's plug in -2 into this function. Now, it's again a constant function. There's no place to plug in -2 because the only output, no matter what, is 3. So we have a 3 there. And what we can do with that coordinate is we can go over here to the graph and we can go to -2 and we can go to 3 and we can put this coordinate on the graph. And what we're going to be careful about is, do we actually have that coordinate? Meaning at -2, 3, is there a spot there? And if we go back to our domain, we see there's an equals to statement, meaning that we can actually have a dot there because we equate to that -2. So -2, 3, and I put a solid point there. Awesome, 1 point down. Now again, if you're comfortable with constant functions, you could draw your horizontal line across, but let's again say you're not so much. So let's say, okay, well, we need a couple more points to kind of figure out this graph. We can find another coordinate within inside this and say, well, what's another coordinate, that x value that works in here? Well, what's a value between -2 and 2? Well, let's maybe pick 0. Why? Why not? So if we plug in 0, what happens when we plug in 0 to this constant function? Again, nothing. We just get a 3. So we can plot that graph, coordinate 0, 3. And again, the question is, why do we have an open or closed circle? Well, everything in between, of course, is equal to, because that's the statement. All right, so again, if you feel comfortable with the constant, you can draw the line. But again, let's say you don't. Let's do one more. Let's say, well, where's the end point here? We end at 2. Now, technically, we don't end at 2. We tend to end really close to 2 because we're not equals 2. But we can still use this to help represent the boundary. So if we plug in 2, what's our output again? 3. And with that, we can draw our last coordinate. Go 2, up 3, but be cautious here. Open circle. Why open circle? Not equals 2. And hopefully you can see there's our graph aspect of the piecewise function. 1 down, awesome. 2 more to go. So let's do number 2 real quick. 2, we're going to kind of do the same idea. Is I'm going to make a table and have my x and my outputs for this one. So I start off with, okay, let's say 3. Now again, technically we really can't use 3 as that domain, but we're really close to it. So we still will use the value of 3, but when we graph it, we're going to use the fact that it's going to be an open circle. So let's put 3 into this quadratic function. Well, 3 minus 4 is -1. -1 squared is 1. Minus 2 is -1. All right. So we can put a coordinate 3, 1, 2, 3, -1. But again, please be careful with the open circle. Now, if you're really good with quadratics, you might be able to say, oh, look, we have our h and k value. That we know this actually, the vertex here is over 4 and down 2. So we actually could put a point there immediately if you recognize the vertex. If not, what you can do is we could pick a couple more coordinates through in here, plug them in, and get some more coordinates to outline that graph. So it really comes down to how comfortable you are. But again, because we know the vertex is here, is 4, 2, that means it is a coordinate actually, 4, 2. It's part of that. And we can go over to 1, 2, 3, 4, and down 2, and there's another coordinate. And that's our inflection point too, or a reflection point, because the vertex we can reflect on both sides. But let's figure out where this thing's going to end. This one will end at our output of 7. So we'll plug 7 in and see what happens here. Plug 7 in, let's get our output. 7 minus 4 is 3. 3 squared is 9. Minus 2 is 7. So we have a coordinate at 7, 7. And again, we want to be cautious here because we don't really have a coordinate there. We're really close to it. So we're going to represent that with an open circle. So let's get that coordinate there. 1, 2, boom, open circle. Now with that being done, we need to, graph it up. Now we're not looking for perfection here, but let's kind of get a good sketch here. We know it's going to go down and it's going to kind of come up. And even then we do know there's a coordinate there too, because they do have reflection on this axis. And we can just kind of bring this up like this. Doesn't have to be perfect, but that's looking pretty good so far. All right, we are 2/3 of the way done. We got one more to go. Let's go over here for number 3. Looking at this one, I can tell this is actually a linear equation. We have our slope, our y-intercept. But we're not graphing it from here. We're graphing from what we have over here already. So again, we're going to go through and repeat the process we've done before. Let's do a table. Our x, f of x. Figure out what our first input in will be 8. And notice that 8 does include the value it's equals to. So let's put 8 in here. Half of 8 is 4. Minus 5 is -1. So we can put a coordinate at 8, -1. 8, -1, and I can put a solid dot there. And we don't really need a middle point here. We don't really need the 9 point because a linear equation has a start, a stop, and a straight line between them. So let's just hit 10 and figure out what we get from there. Put 10 in there. Half of 10 is 5. Minus 5 is 0. So we have a coordinate 10, 0. Now again, be cautious here. It's an open circle. Why? Because it says we don't equal 10, and now we draw our line. So there we have our piecewise function. May not look beautiful, but looks great to me. All right, so we're going to do one more together, and that should be a good balance for you guys to have to work forward. So we're going to do the next example, and I'm going to follow pretty much the same process I did before. The only thing I'm going to be cautious of is here is we do have a square root function, which can be tricky with their inputs and outputs, but we'll wing it. My process will be the same. I'll determine how many functions I've got. 1, 2, 3. I will kind of construct my tables, and from the tables I will use them to, use them to graph. So let's work with number 1 first. So working with number 1, I'm going to create my table here, my f function, my f of x function. And as before, I'm going to use my domain there to dictate my my inputs and outputs, my inputs. So if I plug in -2, what happens if I plug -2 in? Well, -2 times 2 is -4. -4 minus 2 is -6. And we do know this is linear, and because I know this is linear, I can still use just take the last coordinate and use those to connect to make a straight line. So let's plug 2 in. 2 times 2 is 4, minus 2 is 2. And let's use these to make our coordinates. Now -2, 6. And again, we can use a closed circle here because it's a equals to -2. And over here we've got 2, 2. But we want to use an open circle there because, again, not equals to. And we can then connect those lines. Ain't going to be perfect. Really bad. Let's just adjust that a little bit. Close enough. But the thing that's really nice, though, is if you do a better job than Mr. Wilbert did here, you can kind of tell we're on track because this equation has to have a slope of 2 and a y-intercept of -2. Now, I'm pretty close to that -2 there from our y-intercept. My slope is actually not too far off. Up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. So I am on track so far. Let's do the square root. Now, the square root can be tricky just because, you know, we really want to work with input values that can be square rooted. Otherwise, we're going to be dealing with some decimals, and nobody wants to work with the decimals unless we have to. But luckily, you have your calculator if you need to. So again, a good estimate is what we're looking at. So I'm going to start with my 3 here, and I can plug 3 in. And let's see, 3 minus 3 is 0. And actually, that's a good thing because we can take the square root of 0 and get 0 plus 2. Puts a coordinate at 3, too. And now we could try to get a value in between these two if you want to get. And it's possible, but I kind of looked ahead at this problem. And if you look at this, if you try and need a number here, 4, actually, you could put 4 because 4 minus 3 is 1, and you can't take the square root of 1. So actually, that's not a bad one. If you tried 5 or 6, you're going to get decimals. And decimals are okay, and it's going to be in between. It won't be as accurate, but it's an estimate, so it depends on how comfortable you want to be with that. That's your call. But let's do this. Let's get 7. Let's plug 7 in. 7 minus 3 is 4. Square root of 4 is 2. Plus 2 is 4, and I can work with that coordinate. And so let's graph these two up. 3, 2 puts us here, and that is still going to be another open circle. And 7, 4 is here, there, with another open circle. And you know what? Let's be easy. It's kind of it's a raising step. A square root function kind of rises up that way and looks good. It's got an inverse square root, so we're good. And then our last one. Let's do this one. This is a constant function. Mr. Wilbert's going to be a little bit faster here because after the example we had previously. Our constant function says between 8 and 10, it's a straight line. So if we want to do a table to keep track, we can do that. But it should be really quick. We can plug in an 8, we plug in a 10, and no matter what, 4 is our output. So we can do 8, 4, and that's a solid dot. And then 10, 4, open circle. And there's our line. So my hope is that kind of gives you at least an idea of a strategy you can use to help graph some of these parts and work that way. And of course, if you find easier ways or feel more comfortable with using the functions and the aspects of them to do it faster, go for it. Otherwise, good luck.